There's something that got disconnected.
No, that is fine. Earlier I had turned on the microphone, but it was not connected. Because I had the pen drive on.
So, welcome everybody online and offline. We are starting the session. Please get to the screen. Chirandar would have shared a file on the Teams session. Please download it and folder of your Linux where MicroSim also exists. You don't need to be inside MicroSim, you can be outside, but you need to be in the home folder of MicroSim. After you have done that, uncompress the file such that the folder containing the files are available to you, and open this in the security shell that you have got. So just let me go around and check that we are able to put this.
Yes, I think that.
Able to come to the screen? I don't know.
Yeah, right. Extract the file to the MicroSim.
No, so you just extract it in the folder where MicroSim exists. You know, it can be outside MicroSim, don't need to be inside MicroSim. But in the same folder where MicroSim is. Okay, so it's in the MicroSim is in the home folder. In the home folder, you put this. Okay, want to get here? Are you? Okay, everybody there on this screen? Anybody not there on the screen? Just raise your hand so that I don't know. Just can go to you. Okay, so all of you are there on the screen. Okay, so after you have this, what we will do is go through the procedure of creating a instance of the software. All right. The file is essentially an input file. I'm calling it an input file, right? Calling input file, and this contains all the information about the parameters required for the software. What are these parameters? A bunch of those model parameters that we saw for the past 2 or 3 days will be input in this text file. Okay. So let's see what these are. So there are different ways you can create int files. You can generate a new int file from scratch. You can import a new int file, or import an already existing int file and modify it, and you can do both. Okay. What we'll be doing is importing an existing int file because that makes our job easier because already parameters exist, which you can modify and then work with. So let's click on this. When you click on this, you will get to a stage where these tabs open up. Do not click on any other tab, just click on the network module. Okay. And choose int file. Okay. It will basically tell you to go to a directory or from where you want to basically import the int file. So here to navigate to the place where the sys directory that got uncompressed is, go into the sys directory and try to get the. So let's go there. Again, the sys directory is here. This is connected. You should be able to see these folders in the uncompressed thing. So we will be starting with something very, very simple. This model system function F1. Just go inside this folder and essentially click input.in. Okay, just put input.in and open. We should get to this stage. Okay, tell me when you have got to this stage. Are you all able to go get there? Open the file. Okay. Are you able to open? Open this info. WSL. Then were you able to open it the other day? Okay. Able to do. Yes. Just 1 second. With some classes, you can see. Again. Able to open? Okay, so for whoever has been able to open, okay, you will now see that it is showing a grid of this type, and there are some information over here. So essentially, it shows dimension, mesh x, mesh y, which essentially what is the dimensionality of a problem, and what is the size in number of grid points in the x and y grid. Okay. So we are doing a small simulation over here with 200 grid points in the x direction, 200 in the y direction. All right. So if we, for example, change this to 300, it will change this. Then we will do this. So there is a feature over in this whole GUI. If you are unaware of what this any particular key is, you can just hover around here for some time, and it will tell you what it does. Okay. So for example, here it is telling this can take values 2, 3 for 2D and 3D simulation. Okay. So it will tell you what is there in the manual without you having to go into the manual. Right. Then these are geometrical dimensions, and you can go to discretization of space and time. And here you will essentially see the discretization. We are doing finite difference. This particular solver does a finite difference discretization, and then does a time integration. So that's why you take dx, dy, dz. Dz is irrelevant over here because you don't do a 3D simulation. So nevertheless, it's input. And this delta t is the time step that we input. So we have put 0.08 over. Right? So we go next. Here is the number of phases. Okay. So here we are doing solid and liquid, alpha and beta, and you can essentially so that essentially specifying the number of phases that you are doing and number of components that you want to. For 2 phases is the binary simulation, right? You can change phase names. At the present, you will not do that. So if you click over here, for example, you can change these names. These are proxy names. These are just arbitrary names. They don't have any thermodynamic relation. What will come as a thermodynamic relation as the And the same for the component names. Here I've given some arbitrary aluminum copper, but you can also name it as G or. Here it tells you basically how many time steps you want to integrate. Smoothing is essentially something we refer to as precondition. Okay, so you don't want to start from a sharp discretization. That means alpha and beta when you initialize the domain, you have a step function going from the alpha. Typically, that is a slightly difficult thing when you want to numerically integrate. So you can do sort of a preconditioning, and the preconditioning is typically a Laplace based, which is what is done with a smooth. We create an interface before starting. Saving the frequency and saving data. So, for example, I am running a total of 1,000 time steps, and I'm storing every 100 time steps. Right? We have 10 files at the end of this. It slightly increases. Most of you have decent numbers of CPUs. Okay, these are not relevant right now. This is relevant if you restart your simulation. One, then you have to provide the time at which you are restarting the simulation. You go and search for that file, read the information, and then restart it. Similarly, you're starting right? Everybody until here? Go next. Here is where a bunch of material properties get need to be populated. So you have diffusivity and elasticity. So you need to populate these properties for both phases that are existing in the system. You have two phases, alpha and beta. So you need to put these properties for both of these. All right. So alpha, beta. All right. Presently, you are doing a binary simulation. So in a binary simulation for the diffusivity matrix, you can only input one value, only one value, because it's an interdifusivity, and you can only take one value in those for a binary. You will go into a ternary, you will see there are two options will light up over here, because you can then input 4 values into the matrix because it's a 2 cross 2. So there it will ask you for 4 values. If it's a full matrix and if it's a diagonal matrix, then you click on this. Okay. Here it is by definition a single value, so diagonal matrix. So next is we can specify eigenstrain of the space, which is a stress-free strain as you have been exposed to today for both the alpha and beta phases. And if you were to do elasticity or problems related to elasticity, you can specify 3 different ways of inputting the elastic functions. So you can hover over here a little bit and it will tell you what these are. So these are referred to in the white potential as you have the problem.
We have 6 values for in the eigenstrain.
Yes.
What are those?
Here are the matrix. No? So you have the epsilon 11, epsilon 22, epsilon 33, and you have 6 values. So it's a
Symmetric matrix. So instead of 9, you have only 6.
Yes.
okay, good. So next you go to gamma and other constants. Gamma is essentially the interfacial energy.
Diffusivity value, you have to enter something, right?
Yeah, so alpha is 0, beta is 1. So we are going to be having one-sided. Right? So next we go to gamma. Is essentially you have 2 phases, so you can only have one. So it will ask you for only gamma 1. If there are more number of phases, it will ask you for all the possible combinations in this. Right?
You have some unit or dimensionless form.
In the present form, in the present infile, everything is dimensional. But I will also go through dimensional infiles. So if the infile is dimensional, it will take dimensional values. So dimensionless, do it. Okay, so here these are all the dimensionless values as you remark. So gamma is the interfacial energy, gamma 1, 2, one interface. Gamma constant and the polar volume. Okay. Then we go to functional properties, and this refers to the thermodynamics, the way you are interacting with them. Okay? And we will use a function over here, which is 1, which is a toy function. Okay? It allows you to create any sort of thermodynamics that you want. You can create with any sort of phase diagram. If you have seen some phase diagram in literature, and you measure the liquidus slopes or solidus slopes of that thing, you can essentially create that phase diagram over here using function f1. Okay, you don't need any more thermodynamic information to create that. So here, what we put by hand is the A matrix, but in this case, you have the A function directly. So A is, remember, we were doing in the thermodynamic coupling, A is related to the curvature of the free energy or the NTM of the field. Okay, for a binary case, it's a single value. And what I'm doing over here is I'm attributing the same ACN for both the solid alpha and beta phases. It means they are equal. Okay. Next is going to phase properties, phase composition. And this is telling at the given temperature, what are your equilibrium compositions. The temperature that you will have will be input later, but presently at temperature of equilibrium of consideration, what are your equilibrium compositions? So you have to provide them. And remember, you are just doing a binary simulation, so you'll only take one. Let's say you are doing ternary, here you will have to provide multiple values for the 2 components. Here it's first. And then you can fill this compositions either equal to the C equilibrium or different from it. If you are equal, then you have to provide a driving force only by under. Okay. If you want to, let's say, simulations at the equilibrium temperature, we can only provide driving force by giving a filling concentration which is different from C. Right. So there are 2 ways to give driving force. Right. One by underpulling, one by super. So if it gives C filling different from C equilibrium, you can achieve the same. And then you have the slopes. These are referred to as the slopes of the coexistence lines on the problem. Here there is one coexistence line referring to the equilibrium compositions of alpha, and once you referring to the equilibrium coexistence line for beta. So you can provide these slopes, which are arbitrary numbers right now. As I said, it's a pi model. You can create stuff. Okay. Everybody have to be there. Okay. Then with respect to boundary conditions. Okay. So as you have seen what we solve for the field, we solve for the mu, and if there is elasticity, you also solve for displacement. Okay. So you need to provide boundary conditions for each of them. So what I have presently done is given boundary conditions arbitrarily. So for example, if I go here, it will tell me for which boundary I am attributing the boundary condition. You see the red line lighting up? It tells you for which boundary I am attributing the boundary condition. In this GUI, you have only PVC and NVC. In the actual release, you have multiple more possibilities. But in the GUI, you already have just a PVC. So we will put PVC for now. So similarly here, we have X minus and Y plus. Okay, you can put different values. If you want the same boundary condition for all values, you can simply use this key, which will put the same boundary conditions for all. Okay. And so the same procedure can be repeated for both field and we have two stainless videos. Is it okay? Any doubts until here?
You're asking to turn on your mic there because this apparently isn't audible enough.
Not audible.
I'm not sure. Can you turn on your mic there?
I can turn on my mic.
Am I audible now? I hope I'm audible now. Anyway. So where is my screen going?
Yes.
All right. So once we have established the conditions, then we go into filling the domain.
So you can fill the domain with arbitrary shapes.
And here you can choose from different possibilities.
I'll show you some. So let's say we fill a cylinder. Okay.
Fill a cylinder because we are filling in 2D. We can also fill a sphere in 2D by attributing one of the dimensions as 1, as we were seeing the other day during installation. So let's do a cylinder first. Okay. Let's add cylinder. So for cylinder, you need to provide the center of the cylinder. So for example, 0, 0. And since it's a 2D simulation, these two values will remain 0. And I will give the radius of the cylinder some value 10. Okay. I will give this. And so what you are doing is you are putting a cylinder right at the corner of the simulation domain. Okay. And you click the button save. So it will fill a line in over here, which is the same line that will be filled in the actual text file. Slightly different. It will read fill cylinder equal to, but never necessarily this is essentially the information that is going in. So you can fill multiple cylinders. For example, you can fill one more cylinder over here with a different point. We are doing 200 cross 200 simulation, so 100 cross 100 should be possible. So we can put a one more over here. All right. Let's check how many. Yeah, we are doing 200 cross 200. Can certainly do that. Okay. And if you don't like something that you have filled already, let's say you are not liking, you can click on this and you can delete. All right. And modify it and go ahead. All right. If you have done this filling, because you have to nucleate phase field, as you see the composition, I mean the free energy, as you have seen in the evolution of both the functionals, whether you do Allen Kahn or Kahn-Elliott, the free energy always continues to go down, right? By design, nucleation is a energy climbing procedure. You can't do that in phase field. So you have to input nuclei by hand. What you study in phase field is growth, okay, and competition. Any nucleation procedure has to be distributed by hand, right? They can be small nuclei. They need not be big. They can be small nuclei above the critical size, critical radius, and if they have the right conditions, they will grow. Okay. It essentially means 10 grid points that I'm attributing to the size.
Also, there is nothing wrong in nucleating.
Yes.
If it was not stable, it should be.
Yeah. So that's what you typically do. You basically put in, even if you were to do it during the simulation by hand, you can say, okay, this region is rich in this composition. You expect nucleation of a particular phase at this composition. You can by hand put in a nucleation to test whether the phase will grow there. I can put arbitrary shapes. That shape is not really important. I can fill a cube cylinder because these are really going to be very small. And finally, when they grow, the shape that they will take is dependent on the material properties that I ascribe. So the isotropic, if it's isotropic thing, whether I start with a cube is not important. It will take a circular shape by the time it is starting to grow because it's an isotropic situation. It's just for fun. Okay. So people want to play around with shapes, right? So Z, it's a 2D simulation. That's why the Z is irrelevant. Yeah, so because it's isotropic, you will eventually get to a circle if it's isotropic. If it's anisotropic, you don't know where it will go. Depends on the anisotropy. Okay. No, it doesn't matter. Because as I said, during growth, the dynamics is dependent upon the interfacial energy properties that you provide. Irrelevant. Irrelevant. So the point is the starting state is only relevant for the initial transient. But your simulations that you do are typically long term. And they typically are not correlated with the starting state. Okay, very good. So we have the two cylinders that we want to put in. And by the way, there is another option over here. Let's say you have a very, very complicated filling file where you have done a lot of filling of different types, some random pattern filling and so on. It is relevant for some of the simulations Chirantan will show in the following days. If you have such a filling file scripted from a separate software, you can import that. You can import it and it will just populate this space. That will happen. Okay. Good. Let's go next. And here we are going to be selecting some material specific or model specific parameters. Now, the relevance of this particular thing is going down as we go into the more into the as we move our software becomes more mature, as you will be seeing, as we have a nice synergy in the number of parameters that we put in. So a number of model specific parameters are going down. So in the future releases, this will essentially disappear. Okay, because all the models are coming together. So next. So these are all the sorts of model specific parameters. This column here lists out parameters related to what type of simulations you're doing. So if you're doing a binary simulation, sometimes you don't remember in the GP code, I remarked that you have a complicated matrix inversion operation that you need to do to get the evolution of the chemical potential. So if it's a binary simulation, it's just a division. All right. So you don't want to call a complicated matrix inversion code to do that particular operation. So you use keys like binary or even ternary to take care of that. All right. So you just use binary, then it will just do binary. You can specify keys like isothermal, where the temperature is not evolving. So that allows you to do very quick calculations, particularly meant for, let's say, heat treatment or isothermal solidification. All right. So yes, it's a simulation of that type. This write format binary was an old version that we used to write our codes in, where the file format was binary. Binary formats save you a lot of data, a lot of memory, and also the data is well organized. But we have now moved on to an H5 file format. H5 file format is very useful because particularly when you're doing parallel processing. So let's say we launched that simulation that you saw with nearly 20,000 CPUs. So what this 20,000 CPUs would otherwise do is that we have split up the domain into small chunks which have gone to each worker, each CPU worker. Each CPU worker would essentially dump data onto a different folder. And then at the end of the simulations, you will typically have to put all those folders from the information and make an integrated file which you can view. All right. What the H5 format does is that you can specify one single file, and the file, worker will be specified to write in that location of the file where the data needs to be written. So you just write into a singular file, but the worker knows where to write it. Okay. So that way you don't have a bottleneck with respect to how the file information is coming in for the file writing. Otherwise, file writing can become a very serious bottleneck when you have more than 10,000 or 20,000 CPUs. Okay. So we adopt this H5 file format, which is typically used for most advanced software that you have today. Okay, these are keys that we will see as we go along. Presently, elasticity is off, which means we don't have any coherency stresses input just as yet. All right. Track progress, as I think Chirantan remarked the earlier day, is for writing out log output of your solver as you are simulating to see whether everything is going out okay. So it will print out values like what time step, what is the minimum, maximum values of the different fields, what is the relative change, cumulative relative change of each of those fields. And if they are in the right range, you know that the simulation is essentially going on fine. That is for the file writing. This is for the log file that I'm going to write during the simulation. Okay, that just to follow whether the simulation is going on fine. Okay.
You calculate things like interface velocity. No, not
No.
velocity. Like what shift, how much it shifts, and all those things.
Not this one. I mean, it doesn't output that information. Well, it prints. That's all. So then you have the phase field parameters. Epsilon is something that is related to the interface width. Tau is internally not used now. This has become obsolete variable. So we will look at it later. I am switching on anisotropy over here. One, all right. And there's only one type right now, 4. But as you will see in the next version, there will be multiple types. Particularly, we will talk about it a little bit more when we come to that in the features in the new release. That now in this particular solver that you have in the on the GitHub, you can introduce only one type of anisotropy that is active for all interfaces in the problem. Okay, but in the new release, what we can have is you can attribute different functional forms for the different interfaces that you have in the problem. Okay, what that allows you to do is something that Shupriyo, when he was here, was remarking about. You can attribute different interfacial energies and anisotropies corresponding to different interfaces. That means you can precisely account for crystallographic differences between the different interfaces. Okay, and this is something which is allows us to do experimentally relevant things a little bit more closely. Okay. So anisotropy 4 presently hints at the possibility that you are doing 4-fold anisotropy. Okay, that means a cubic anisotropy. The strength of the anisotropy is 2%. So typical metallic systems, if you look at metallic alloys, the strength of anisotropy is somewhere between 1 and 2%. Typical solid liquid anisotropy. So this is what you have over here. Okay. Okay, then this is with respect to potential. You all know what W is now. The potential function in the functional. Now there are different choices over here. One is the choice that you have written and used extensively over here, which is a double well type of function, which is phi squared into 1 minus phi the whole squared. You have been using that all through. But there is another possibilities, or there are other possibilities that you can use. For example, I can use something what is referred to as double wall potential, right? Where essentially you have, instead of a smooth variation between the 0 and 1, you have a wall type potential, right? A parabolic potential in between. Now, why do you do that? It has to do with certain artifacts that we have when we have multiple phases. When we have multiple phases, you have something like third phase adsorption at interfaces, and that can be restricted if you have this type of potential. All right. I will describe this a little bit more when we do multiple phase examples, but right now just take it a while. There are different possibilities to have functional forms of this potential. All right. Okay, this is the equilibrium temperature in the system. We are non-dimensional, so we have taken the equilibrium temperature to be 1. The filling temperature can in principle be different from the filling temperature if you want to restart your simulation with a slightly different temperature than what you have. Presently, we are starting the same simulation, so this is 1. And this is essentially providing you some undercooling. Okay, so you are starting at 1, you are 0.96, so you have 0.04 units of undercooling in this scale. All right. Okay, so this is all okay. And so shift is something that I will talk about when we are doing a simulation. So what this key allows us to do is that when you are doing a simulation, you can retain the same number of cells in the domain on the solid. Okay, and I will show you an instance of that. When you see that, it will become something which is really easy to appreciate. I can tell you what it is. You saw that simulation that Professor Fanikumar showed, in which you had that chaotic fluid flow formulation, right? You saw that the solid evolved to a point and then it didn't evolve at all, right? What is happening is now, after moving to a particular point in space, I am essentially moving along in frame along with the solidification interface. So essentially my frame of reference is now with the interface, so I don't see any change there. All right. So what that allows me to do is, if I shift that frame of reference like that, then in that same box, I can simulate for longer. Otherwise, I have to go and increase the scale size of the box as we go on, which I don't need to do if I do this. So if shift is 1, I'm essentially making use of that ability. Flexibility. Okay, noise is for adding noise at the interface, particularly to do with dendritic growth. If you add noise, you add fluctuations. They are essentially mimicking compositional and temperature fluctuations or energetic fluctuations that you typically have in experiments. And if you impose them, you can essentially encourage dendritic growth. Right composition, remember this is relevant for the GP model because we are solving for the chemical potential field. You can choose to write the composition or not write the composition. If you choose to write the composition, you can also visualize the composition. So if I set it to 1, you can set it, write the composition. What is that? No, so we are doing beautiful, smooth calculations. So the amount of noise we actually have is very small, very, very small. Yes, precisely. Again, as you saw the simulation that you had a planar interface just moving along steadily. That got destabilized suddenly. Won't have noise. Yes. No. Okay, so have you all come to this stage? Okay, so now we are come at a stage where we need to put in a name for our in file. So we are doing Chalakere, we are at Chalakere, so just write Chal, and then we can say GP, and well, GP would give us a very bad thing because we are doing multiple examples. So GP1, and then this and output. All right. Make sure you give some names, and you generate in files. Click on this generate in files. It will guide you to a place where you started to take the in files from. Okay, just choose that place itself, and it will populate. Please fill all values of the rotation matrix. It is asking this because I have turned on the rotation. I have turned on the anisotropy. Okay, as soon as I turn on anisotropy, remember I can rotate my grain arbitrarily. So unless I specify the value of this, the information is incomplete. So I need to go back essentially and fill this value. This will be there in the material parameters. So click material parameters, and here you will see this value over here. Just follow me over here and fill it as 0, 45, 0. Not this. This can remain 0, it is essentially this one. Ideally, you should not be asking this, but will I put in? Yeah. Just put, actually one we should do. Just put 1. 0, 1, this phase 1, phase 2, just put it over here, 0, 45, 0. No, sorry, not this way. 0, 0, 45. Just put it in, I'll tell you what it is. Okay, so what it tells you is that I'm rotating my dendrite 45 degrees about the z-axis. So remember, you are doing 2D simulation. So the z-axis is here. So you're rotating about z-axis by 45 degrees. Correct? Huh? Really? No, I don't know. I don't think so. Not. So let's go ahead. I still need to fill. That's not good. Well, he is right. We need to fill. Then just fill as I am filling. Okay, so after you fill everything, it should come to this stage where it says successfully created input and filling files as following. Okay. Everybody get to this stage? No? Yes? So you click OK. And now what I'll be doing, just see what I'm doing. You will do it differently corresponding to what you learned yesterday. Yeah, I can press run. They cannot press run. So don't worry about it. I will show what runs through the GUI. You have gone through a different way of installing, which is through the Singularity. In Singularity, the run command doesn't work, but you can still run the solver as he will show you how to run. So Chirantan, after you do that, you just write down what they need to do for running. I will run in the GUI, okay? That is for the HPC, okay? That will do it automatically. Okay, so when you run it, you should see something like this being output on your screen. Okay, so you see that the time is essentially going. It's running for you, Anindo. Also, you're running. It's running. Okay, did it complete? Okay, if it completed, then I'll just put clear so that we can come on the top here. Huh? Yes. Time is real time. I mean, so time is delta t times. Okay, so now something would have been written in your data folder. So CD data. Go here, check. I will do control minus. So something would have been written like here. Output chara GP1. Something like this would have been written now. Do you find this in a data folder? It runs, sir. Now we don't know why it runs. So output chal GP1, this one. This should come in your data folder. CD data. Put ls minus LTR. There. Okay, so there should be 20 files corresponding to the 20 simulation files that you ran. Okay, done? Everybody getting until here? Okay, so notice this file name that you have. It's important to keep track of that. I'm going to type a command, you just follow me.
The one.
What?
The underscore one also.
What underscore?
In the file name.
Underscore one, sorry.
Where the global command, you can just pass on the data directly to the
Okay, so go here, and if the global command is working for you, just type the global command. Otherwise, do what I'm going to be doing. Okay, type it like this. If you have the command, the microsim underscore write xdmf command working, just type microsim underscore write xdmf and followed by input.in, tell this .in, the output file name and the starting time step and the end time step between which you want to create the files. Okay. If the microsim gp write xdmf command is working, just use that instead of what I would do. microsim gp is working for you? microsim gp write xdmf?
So if you have your MicroSim directly in home and MicroSim will work.
Okay.
It's not able to look at the master path.
Oh.
I have corrected it, but it's in the middle.
Okay. All right, so I shall assume that you can work here and it should give you, once you put an enter, it will read processor 0 reading in 5, okay? And after you have done this, do cd data to check whether the operation has been completed. So there should be a bunch of .xml files that have been created with the same extension that you had before, and see I have done a mistake. All right, I have done a mistake over here. My output file had a small o output child gp1, whereas what I have created is with the capital O. Okay, what it will do is the following. It will not create an error here, but when you open in ParaView, it will try to open a .h5 with this file name. It will not find, and it will tell it does not have any data. Okay, so you have to correct for this. This can be corrected easily if you have done this mistake. So what you have to do is to rm star. This will delete all the .xml files that you just created, and basically you go back and repeat that command that you just wrote down with the right value over here, which is a small o. Okay, and then you check again that you have the files with the right extension such that you can run it. All right, fine. Come until this stage. Okay, just one second. So in the write xdmf command, you just provide the Jonathan, what have you done to the write x? Huh?
That does not mean anything. If data is directly there, it should work.
If you do the microsim write xdmf command, you don't need to do anything. Then you need to do this. So all of you have been able to do this by behind? What? How to get this means what? You type it in. A path. Yeah, that's what. So Just check if write XDMF is working. Just type write XDMF tab. Okay, if it's not working, do tilde microsim tab, grand tab, and then tab write XDMF. Yeah. It's writing the XML files. Is it's working for you? He has a Jonathan. He has an issue. He has an issue. You're able to do? It's done. Huh? Okay, so I will assume that all of you are able to do. Huh? Whatever. So then you go to the data folder and write paraview. Write paraview and open. Okay, so it will open something and go here, and you would see two types of files over here. So here you click on this entire tree directly. Okay, and choose XDMF reader. Okay, and apply. Okay, you will get something like this. Okay, and then you do see what comes. So the small ones are shrinking away, only one side is remaining. What happened? It just grows a bit small, only a little bit, because the undercooling is very small. Okay, so you are essentially seeing the capillarity effect into play. Okay. Are you all able to get to this situation? Who is not able to get until here? Yes. You able to get until this point? Okay. Huh? Okay, everybody. Still not working? Okay, so for whom we're already working, you see, you can play the movie over here. A very small movie, but a movie nevertheless. Why do you see a shape like this? No, shape. Yes, precisely. But why is it a square and not a diamond? You rotated by 45. Okay, that is why it's looking like a square. All right. Otherwise, it would have looked like a diamond. Okay. So to test that, so first we'll make it grow a little bit bigger, right? So close this and go to your place, this GUI creator, and just in the material parameters or the model parameters, just go there, go next. Here you go back, because you see that the thing is shrinking, right? It is shrinking because the size that you have input is too small. The capillarity force is too large for the driving force that you have put in. Okay. So we will increase the undercooling over here, make it 0.92. All right. And then go ahead. Now we are increasing the undercooling. We are decreasing the temperature, increasing the undercooling. Okay, and then here and generate the same in file that you had before, or maybe 2, just to keep a record of what you had. Put 2, put everything 2, and then first generated the in file in the same place that you had here. Choose generate the in file. You should get successfully created, and then put output shell gp2, a separate file name to what you had before, and then run. Only one group is not doing. You're able to get to here? Pretty though. No, the same size. I am using only 4 CPUs in my. I can use 8, but in the script it is used hard coded to 4.
What is there for the laptop?
Okay, so it would complete. And then we will go and do the same procedure as before. Okay, just get it in a different terminal. So what happened? They're not running? Huh?
In Malawi, it will show three, I think, examples are previous, right?
XDMF, choose.
We always select the top one.
Yeah.
Here only two, and both are in the
What is the ParaView version? No, but they use Singularity, no? They are inside the Singularity. So they should be using the same version of ParaView than everybody else. Okay, so now you would have seen something like this. You have increased the undercooling and now you are growing peacefully as a cube. Okay, please get to this stage. After increasing of undercooling, you should come to this stage. Okay.
Now we are seeing a square.
Yes, because it's rotated, 45-degree rotated, right? You'll get a diamond if you are 0-degree rotated, but this is 45-degree rotated, so you'll get a cube, right? So if everybody get how many? Just raise your hand. How many got till here? Okay, very good, very good, very good. So they have got. Oh, it's running. Okay. No, I have initiated at one at the corner. So take a chalk and just put it underneath. Just take a chalk and put it underneath. That is enough airflow for it to be quiet. Enough. Everybody able to get to here? Most of you? Okay. So now you can check what is their outputting. You can click here. There are different things it is outputting. One is composition, which looks like this. All right. Then this is mu, which looks like this. All right. Then alpha and beta are just the reverse of each other. So that's no fun. All right. And you can do something nice. So our composition profile looks like this. I mean, there are several things plotted. So we can choose to plot what we want. Let's not plot mu. Let's plot this. Yeah, so this is what your composition profile is. So you have, so why do you see the dot in the center? Can anybody tell me that? Huh? No. Why do you see this dot in the center? Yes, but why did it remain as a dot? Is 0. So this is a thing that you see, because solid diffusivity is 0, anything that is in the solid will not evolve with time. It is frozen. And that's why segregation is important. In that classical experiment also, when you are solidifying, it will retain all the solidification history in the dendrite, and that will be frozen in time. Okay, that is essentially what is happening in the simulation as well. Okay, in a precipitate simulation, you don't see this. Why? Because you have diffusivity on both sides. No, red one is the starting solid composition that you started with. That is slightly off because you're starting with the equilibrium composition, and then you are at the undercooled temperature, so it will take a new composition with which it will grow. So it's different from this, but there is no homogenization that is happening between the two because there was no solid diffusivity. It will take the time scale of in this particular case, infinite time, because solid diffusivity is 0. If you do a finite diffusivity of the solid, you will see finite time in which this will diffuse. All right. You are able to do? What happened for you? No. Inputting is not? Oh, where is your partner gone? Your partner went and sat in the middle of both of them? Okay, yeah. Jonathan will help you. Get that running. Okay, so for all of you who have finished this exercise, go back to your file, and just for fun, in the material model parameters, go back again and not the model parameters, sorry, material parameters. 20,000. Go here and change this value to 0. Instead of 45, put it to 0. Okay. And rest of the things you can just keep the same. And put 3. No, keep it the same. 0.92, delta T is 0.92. T is equal to 0.92. Generate the files. And then run. 0.92. T equal to 0.92. So equilibrium temperature is 1, filling temperature is 1, T equal to 0.9. Okay, and run. Akash, you are able to do? Chandra? Okay. So now we'll run the same command. Thankfully.
She's going one step ahead. Once we-
So almost everybody able to do it, right? So just to confirm my hypothesis or explanation that I just gave you with respect to this guy here, you can try to change d is equal to 1 and see what happens. No, don't put d equal to 1 right now. The anti-trapping current is on, so d equal to 1 will not be of interest. Don't do it. It will not give you something. Okay, so what is the next task? The next task is to close this and to go to, let's do something realistic. Okay, so next task is go here to your GPU, to your GUI and go back here. Okay, we will import a new int file. All right, we'll import something here. Right, so again the same steps: grad potential model, choose int file, and essentially go to the place where your int files are there. Remember this sys folder. So go to sys chalakere or sys as you have it. And what we will do is choose aluminum zinc dendrite. Okay. Over here. And in this, you basically select input underscore aniso.in. Okay. So it will tell, oops, I have noticed some missing. Don't worry about it. Just go ahead. All right. All right. So first thing to do is to change the size of the simulation a little bit. Make it 200. 200. Okay. And all of these values. So now you see, sort of, as you will see, sort of, as you see now over here, these are dimensional values. Okay, in this in file, and these are now in units of meters. Right, so the units of the simulations are essentially the units of which you input in the in file. Right, so you know what these values are. Right, what is it? Because you are making the in file, no? So you know what values you put. Yes, so you know when you are putting the number, whether you're creating a dimensional in file or non-dimensional in file. I mean, the in file is created by you. So if you put a dimensional number there, it will be a dimensional in file. In file actually doesn't know dimensions in principle. It knows a value. And if you as a user have put in values to correspond to a dimensional simulation with those specific values, it will be essentially corresponding to those values. Okay, the scale of the simulation is something that this is decided by you. Dimension is decided by you. We do not do an inherent dimensionality check inside the solver. It's consistent and in the same scale that you put in there. Okay, so let's go here. All of this is something that you have gone through, so but we will just check number of phases to this 2. Go ahead. We'll do the same thing. 20,000 time steps are sufficient to get information. And here you see I have chosen an alloy composition from some place. Okay. Now I will tell you how we chose this alloy composition to correspond to something. Okay. So, aha. All right.
So this is a real world.
Huh?
This is a real world.
This is a real one. Yes. So aluminum zinc dendrite in this folder, essentially there's a TDV's encrypted file. Okay. So now this composition underscore FCCA1, which is the FCCA1 is the name of the solid thermodynamic name of the file. Okay. So if you open this, if you open this, you will see that same file that I was showing you before. At a temperature, you have the solid and the liquid positions tabulated in this manner. Now, what I have chosen is an alloy, which is here, 870. So the melting point of this alloy is phase 870 with this as the solid composition and this as the liquid composition, equilibrium. So it is present in this file. And this, where did I get it from? You can get it from different places. You can tell Panda Thermocalc to do a line calculation for you for a given alloy composition. It will do it and tabulate these values. All right. You can also ask PyCalFat to do it. It will do the same. All right, and it will provide this text file for you. So therefore, this is essentially what I am reading, and when I'm creating my values, I'm filling with the equilibrium values at that temperature, which is 870. Okay, so these are the solid values, and the rest of them are the liquid values. Okay, I'm rounded it off to third decimal. This C gas is not really relevant for us. This is something that we do for when we use function F2. All right. So here as well, I'm going to give a rotation of 0045, which is a 45-degree rotation about the z-axis. And then I'm going to go ahead. So here I'm going to do Neumann boundary conditions. Okay, previous one was all periodic boundary conditions. So I'm now going to do all Neumann and check what we get. So what shapes do we add? Cube. Huh? Let's do random. Although I've forgotten what the random thing is. Anyway, we have to look at the manual. Oh, there is somebody has been nice. So precipitate 10. So precipitate radius, let's do 10. So it'll do a random filling, huh? So volume fraction 1%, 10%. Spread is all right. So let's do this. All of these parameters can remain the same. And let's create our fourth in file. Generate in file, the same place as this. Here, and run. We're doing something. Are you all able to get the input file and get it to run? Okay. So now you see the time steps over here. They are, because of the realistic time, you are now essentially doing a few microseconds in simulation. So also you see that these two guys have saturated. It's telling that some sort of steady state is there in the problem. By the way, there's some tea there. So if all of us are feeling sleepy, we can take a small tea break after this, and then there's glass also there. No, you do the tea. You take for yourself. Do. Take. No, after this example. Point one. Huh? Yeah. Wait, tell them we are taking a wait after this. Wait, after this. Let's go back. Yes. This next step we will do that. Yes. There's tea. Yeah, the percentage change over the what precipitate radius you give. So if you give 0.1, so 0.1 times 10 plus minus. Your grades, yes.
So what happens if the physical radiation field distance does not match up properly to,
It will keep searching for the right filling.
and it will just
Yes.
keep running, right?
Yes.
So you should think this one is function. It has some stage error.
Spread is essentially you have some average radius. You give a noise about that, plus minus. So there's a randomness in the size as well. So this is the filling it did. Okay, so you should be able to get to this stage.
Very nice.
This is because
Because of
the boundary conditions are.
what?
Normal.
Normal, yes. 90 degrees. Are you able to all get, you should all be able to get to until here. We'll take a tea break and then explain what is going on here, all right?
This is aluminum.
Zinc with a 45-degree rotation.
No, the five is that.
Element. Just stop recording.